Okay, YouTube, this is my first video in a module that I'm doing on linear programming, or specifically optimization. So let's go ahead and start by defining what we mean by optimization. In mathematics, I pulled this definition off of dictionary.com, but it was sufficient. We say it's a mathematical technique for finding a maximum or a minimum value of a function of several variables subject to a set of constraints as linear programming or systems analysis. So basically what I'll mention here is that we have some objective function or something that we're trying to make as big or as small as possible, the maximum or the minimum possible value of that thing, but subject to constraints. So when we refer to constraints, we're referring to a system of linear inequalities that basically surrounds or binds what we call a feasible region of solutions that might potentially satisfy the system in the first place. So when it comes to linear programming, essentially what we're going to be looking at are its parts, and its parts consist of these. Some objective quantity, or I'm going to say in terms of objective here, maybe I'll do this here, see if I can help myself out. In terms of an objective quantity, we say that this is our goal function here, our goal function that we want to make as big or as small as possible. So this might be profit, which in this case I would want to maximize, or cost, which in this case I would want to minimize my cost. So we have a goal function that we're trying to make as big or as small as possible. The constraints are going to be what we refer to as our inequalities. Our inequalities are what we'll refer to as our constraints. So looking at this system over here, let's go ahead and just take a look at these first two parts and see if we can identify them. We say find the minimum and maximum value of this function here subject to the following, and this shouldn't say restraints, this should say constraints. So the parts we're going to label so far are these. We're going to say that this is our objective function. In this objective function, what we're going to do is we're going to find all of the x and y values in this feasible region, and then find out which of those x and y values in the feasible region actually makes this, in this case, as big and as small as possible. So in terms of our constraints, when you constrain something, you bind it in, or you surround it, or you kind of keep it in check, okay? You surround it, okay? So these constraints right here, what they're going to do is they're going to, when graphed, spell out our feasible region, or show us the region in which all x's and y's would satisfy all these inequalities. So our objective function and our constraints, what we're going to do is essentially, with these constraints, we're going to graph them, and then we're going to talk about why we find vertex points, but find the vertices of the feasible region. And then what we're going to do is basically test those vertex points into this function right here and say which of those vertex points made this as big as possible, or as small as possible, or both. So looking at these constraints, I'm going to talk about these first two right off the bat. These are very common, and what we'll want to write here is that, of course, this x equals is a vertical line, and this y equals is a horizontal line. What we're going to do, of course, is graph these as if there was just an equal sign between these. So x equals 0, well, that would just be the y-axis right here. So because I have different colors, I'm actually going to graph in this solid line here at x equals 0. Solid because it's a less than or equal to. One thing I will mention about linear programming is this, as I label this line x equals 0, is that all of these are usually less than or equal to or greater than or equal to when we set up our constraints for a system with linear programming. So our y is greater than or equal to 0 number here. I just want to graph the constraint here. I'm not going to shade yet. I'm going to shade the shading until we're done. So we say y equals 0. So I've got these two constraints on there. Now let's talk about these next two constraints. Now I notice this is what we call standard form, where our variables are on the left and our equation or our constants on the right. To graph this, one really nice method of graphing a line when it's in standard form like this is just for us to go find the x and the y intercepts, or the y and x intercepts respectively here. If we were to plug in 0 for x in this first case, we'd just be left with the statement 2y equals 4. In other words, when x is 0, we get a y value of 2. And likewise, when we plug in 0 for y, we get x is 4. In other words, when y is 0, we get an x value of 4. So these are the two intercepts on this graph right here. And I'm just going to go graph them here. We say 0, 2 was our y-intercept there, and 4, 0 was our x-intercept for this graph. So we're going to connect these two dots. I'm going to graph this in sort of in pieces, try to be as accurate as possible. And then what you'll want to make sure we do in this video, on any of these when we're linear programming here, graphing a set of linear inequalities and seeing where they shade together, is label these. So looking at the intercept method for this as well, I suppose I would say x and y. When we plug in 0 for x, I get negative y is 1, so positive y is negative 1. And when I plug in 0 for y, I get x is 1. So we get 1. And I'm going to go ahead and graph these 2 points. So we have a y-intercept at negative 1. We say negative 1 is right here on the y-axis, and then an x-intercept at positive 1. I noticed this would be a line with a slope of 1, so maybe I'll graph a few extra points here just to be accurate. So go ahead and put this in, and we are going to label it. So far, all we've done is really identify our objective function and our constraints, and we've gone to graph the constraints. So x minus y equals 1 here. So what we're going to do now is we're going to go back and we're going to shade our feasible region here. And the way we're going to do that is just basically by testing a point. Now for x is greater than or equal to 0 and y is greater than or equal to 0, I don't need to test a point with those to tell you that if x is greater than or equal to 0, we're talking about all of the x values that lie to the right of that constraint. And we could test a point. We could test, say, 1, 0. But when you plug 1, 0 in for this right here, you'd plug 1 in for x, 0 in for nothing here. There's no y. And you get 1 is greater than or equal to 0, which would mean this point's true, so we'll shade toward it. And also I could say that clearly this is y is greater than or equal to 0. We're going to shade above this right here. So you can see how we're kind of trapped in the first quadrant. So what I want to do is I want to make a little note here. These two right here that are common right here, basically they restrict us to quadrant 1. Restrict us to non-negative values. And when we start looking at application problems, basically what we're going to find out is that we don't often get negative values when we're talking about maybe how many models of each type of bike to produce or something like that. So when we look at this here, I'm already trapped up in the first quadrant. Now testing a point on these other two constraints, I notice 0, 0 is on neither of them. So if I test 0, 0 into, let's say, this equation right here, and not the equation, but the inequality, but it goes with this constraint right here. I know this because I labeled it. I get 0 plus 2 times 0 is less than 4, or 0 is less than or equal to 4. So this is very true. So for that equation right there, that constraint right there, we're going to shade toward the side of this graph that contains the 0, 0 point, since that was a true statement. Now when we test 0, 0 into this second equation, we get 0 minus 0 is less than or equal to 1, or 0 is less than or equal to 1. We also get a true statement. So this would shade towards 0, 0, which happens to be on what I would call the above side of this right here. So in terms of what we've accomplished so far, identified the objective function, we know our constraints, we graphed our constraints, and now we've shaded. So let's identify the feasible region. So I would identify the feasible region. Let's switch over to like a greenish color here. Would be this inner region right here where they all sort of shade together. And I'm going to try to shade this as best I can. You can kind of see that we get this four-sided polygon right here. And so the feasible region is defined right there, and I could say that maybe I'm going a little crazy with the green here. Maybe we'll switch over to like a, let's do this. Ooh, why not? Oh, we kind of did that. How about a dark purple? Its vertices of the feasible region are what we're going to be after. So what I can tell you is essentially this. For the sake of this problem, we're trying to make this objective function as big and as small as possible using any pair of x, y that come in this green region. So we're just going to plug in all of the points in this green region into here and say which one made it as big and which one made it as small as possible. The only problem with that plan is that there are infinitely many points in here. So what we're going to do is we're going to make a little note here, okay? And that note is basically if a minimum or a maximum of our objective function occurs, it has to occur at a vertex of the feasible region. So minimum Okay, so what we're going to do is we're going to work back through this and we're going to identify our vertices. Now on something like this, I would say this was pretty stinking easy, and the only reason why is because these were pretty straight up points of intersection. I mean, this right here, I would say that because it's the intersection of this line and this line, I know that the x value is 0, and I knew the y-intercept on this was 2, so we say 0, 2. Out here, I'm not quite sure of yet. Right here, I would say this would have to be 1, 0. That's easily discernible, and we have 0, 0. So of all of our vertices, the only one we don't have is this one right here. And because I know it has to lie at the intersection of these two equations, then what I can do is I can just go set up a system with those two equations that I labeled on their lines and solve this. Now I'm going to use elimination here, which means I guess I'll go ahead and take the whole second equation times a negative 1. So that when I add these, my x's cancel. I get left with here, I suppose this would be 3y, and then it would equal 3. So we'd say our y value there must be 1. And our x value, if our y value is 1, go plug that back into one of the original equations. We say x minus a y value of 1 is equal to 1 from this constraint right here. So we get x is equal to 2. And we can verify this visually. We say 2, 1. So here's what comes into play now. Once we've found all the vertex points, we're going to test these points in the objective quantity. So I'm going to try to squeeze all this in here. You likely have more room on your paper, but what we're going to do is we're going to make a table. And we're going to put the vertices on the left, excuse me, and then the objective function, in this case, z equals 3x plus 2y on the right. And so inserting all of our vertex values, so we have 0, 0, 1, 0. We also had 0, 2, and we also have 2, comma 1. And I'll try to block this off here so it kind of doesn't look like it's conflicting with this stuff here. Basically what we're going to do is we're going to go plug all of these into the function. So we would get this here in this case, 3 times 0 plus 2 times 0, we get 0. In this case, we would get 3 times 1 plus 2 times 0, we would get 3. Okay, so here we get 3 times blank plus 2 times blank. We would get, in this case, if we plug in 0 and 2, we get 4. And then last but not least, we say 3 times, in this case, 2 plus 2 times 1 is equal to, in this case, we would get 6 plus 2, we would get 8. I'm going to put a box around this, I'm going to put a box around this. And what we're going to write here is our minimum value is 0 and our maximum value is 8. And they occur at these points. So what we're basically going to write here is a conclusion statement. And this conclusion statement, here's what it needs to basically conclude. We say the minimum value of the objective function is 0, and that occurs when, or at, we'll just say at 0, comma 0. And the maximum objective function value is 8, and it occurs at 2, comma 1. So the important thing is that we note here the maximum and minimum values. In this case, we wanted to know both, but also where they occur. So this whole linear programming process is essentially finding the feasible region and then saying which of the points in the feasible region, which have to occur at vertices, by the way, make our objective function as large or as small as possible. Cheers.